Thank you very much. Yeah, as was said, I am front-end lead at Signal, and my name is Tomáš Řezáč. I'm in business
Alright.
for
Вот это я просто хотел, нашел тут.
almost like 15 years, and mostly I work with Angular, also contribute to Svelte currently, but have experience with a lot of other technologies. But today we are here to see what are signals about, and as I believe it's always the best to understand the technology from inside to understand what can some hiccups be when using the technology, and I think it's particularly like needed or good in this case. So this is the outline of the presentation. I will show you what reactivity patterns means in general, just swiftly. Then we will go to the signals and see what they are, something maybe about where they are used and history. Then we will see how they differ from the other reactive patterns by showing some mathematical graph of dependencies, which is used in signals. And we will see some typical usage of signals in like real world, in kind of like some fictional framework. Then we will go for implementation of very, very simple signals with a lot of like undone things, but like functional solution in like 50 lines. And then we will check what are the issues in this simple implementation and check what can be done better and what is actually done better in TC39 proposal, which is a proposal in stage 1 for signals to be native part of JavaScript. So let's check the reactivity patterns in general so we know what is the business we speak about here. I will actually go to this article because I believe that this is like perfectly written to really show what is the reactivity pattern in general about. So reactivity is how systems react to change in data. And there are many different types of reactivity, but for like this specific article and for our presentation, reactivity is when data change. You do things. So when something change, something else react to it and change as well. And let's check what are those like most known reactivity patterns. So we have the PubSub, publish, subscribe, where it's, in this case, the implementation is just simply simple object with subscribe and publish functions, and then some events which hold the subscriptions. And you can see here in the beginning, we first subscribed, so we tell we are interested in this like update key, and whenever the update event is done like under this key, we simply call this callback, and in the publish we say update, and then the message, which actually this data is that called to or passed to the callback here, and it's logged. So this is very simple, probably the simplest reactivity pattern, which is currently not used much because it's like super primitive. Maybe more, but it's pretty like known even for that it actually exists in native JavaScript as well. You can always create event listener and custom event and just pass the custom events to some DOM node and then react through this event listener to it. So it pops up as well. There is some more extended version, which is called observer pattern. What it does better is actually that it somehow splits the observer and subject, which is the things which depend on the other. And what it brings as an extra is that you are now able to remove the observer. So once some observer that don't want to be subscribed to these events anymore, you can easily remove it from the subscription list. And that's way more practical for more advanced usage of things outside some singletons which live forever. So the PubSub is quite okay for it. Then we have some proxies. I think this is quite advanced stuff. We don't need to go through how proxies works, just how to like bind into some side effects when properties are changed in objects. Then we have some reactivity systems. It's actually, we already mentioned this RxJS. it's quite an old implementation across many different languages, like 20 plus languages. What it does like extra, it's do this like observer pattern. This bring possibility to modify those data in which are emitted through this publishing and subscribing. So before the information get to the subscribed, you can mutate it, connect it with other subscriptions and so on. So this is very, very advanced, but you have the idea what the reactivity patterns are, I hope. So let's move forward and see more about the, like, in practice. I always believe that it's the good example is the best to understand the very basics. So let's check here. We have two columns on the left. We have like regular JavaScript. We assign 2 to x, then we double it. As assignment, we change x to 3, and then console log will bring us 4 because the subscription or assignment of 3 to x doesn't change anything what happened before. It's there is no reference. It's just the doublet was already done. On the right side, on the other hand, we have signals, which the value of 2 is now wrapped by some like factory function into object. So x is now some object with some additional functionality. It has the value property, which is actually 2 in this case. When we have this computed signal, it's also a signal, but it somehow magically knows that whenever x change, it needs to recall this callback and assign it to double again. So on the first run, it's just done, the callback is run automatically, so it's will return 4, but whenever we assign 3 to the x signal, it will again call this callback, the double will change, and when we lock the double value, now it's 6 and not 4 as in the regular JavaScript. So this is the very easy example of what signals can do. And now let's check to tell more about those like very basic blocks. We have the signal, we have the computed that we already went through. Just note that the derived or computed signal is actually read-only because you cannot assign any values to it. It's just derived from some other signals. And then we have effect. It was not in the example. It works somehow similar to the computed signal. It just doesn't return new signal, but it only run the callback, and the callback is like produce some side effect to influence another part of the program. It's often used to manipulate with DOM, because for DOM you cannot just by creating computed signal do anything, so you need this side effect. Now let's check more about like history and very basics. So it's known for like fine grind reactivity pattern because every single value has its own reactivity like holder, which is the signal. So every single very basic value can have or should have its own signal. Then the next thing is that it's actually quite old pattern. It's like more than 60 years old when it was first used in something similar to Excel sheets. That time, like without any UI, but it did use this pattern to propagate changes in the cells to another cells, which were derived from them. It has actually been called by different names over time. So we call it signal for maybe last 10 years. And before it had very different names. We won't go through those. But currently, and maybe that's why we are all here, is that it's actually used in a lot of different frameworks, and more are coming. Angular, Ember, Mobix, Preact, Quick, Solid, Svelte, Vue, this. and I'm adding Tailwind. It's actually not JavaScript at all. It's just CSS, but it's leveraged the similar pattern through styled queries, something similar like media queries, which doesn't depend, the styled query depends on some other styles. And also CSS used something like signals under the hood for coping with variables and calc, because you can use calc on variables and then assign it to another variables. And when you change the one which is used in calc of the other, it will automatically propagate and update those dependencies as well. So actually signals are already in CSS without us even realizing that. And it's good to notice that all those frameworks have slightly different API, different implementations. There is no single implementation now which would be like the best. But maybe there will, we will see that later. Because there is this proposal which should bring signals to JavaScript as this like generic solution which should fit to the needs of all those above, like except Tailwind. And the pattern is like the very basic implementation is push-based. So it means that when you assign some value to the signal, as we saw before, it's immediately propagated to the derived signal. And the calculation is done and the new signal with the new value is returned. But more advanced versions are pull-based as well, or push-pull based, like combined, which they only tell that some things need to be updated, but they are only updated once you read them, once you need really the data, because it doesn't make sense to make calculations which are never actually used. Okay, so now this is a cyclic graph. You can also know it from like topological order explanation in mathematics, where you have dependencies which only goes in this case like from top to bottom. So there are no cycles, simply computed G depends on C, but it cannot be vice versa, or there cannot be some like these arrows always go down, it cannot get up. And for some maybe later discussion, there are like two terms, sources and sinks. The source is actually the signal at the top, while in this case, for instance, signal D, but signal which is computed below is its sink, so it's consumed the source. But at the same time, computed D is a source for computed F, H, G, and just the very end of the graph are only sinks. These are again either computed or they could be effects as well. Now I'd like to show you a more realistic implementation of signal usage and why is it actually used in so many different frameworks. So this is again some kind of more like fictional code, because let's say that some of it is written by myself, like declaring the signal, declaring the computed signal, which tells that it derives value each time when the signal change and tell us whether it's even or odd. On the right side, we have this HTML markup with some extra mustache syntax, which is often used in some frameworks. And this tells that actually this is some JavaScript, so the parser of the HTML will get this and connect it to the JavaScript. And just imagine, or it's like it's real in a lot of frameworks, that those values now, when the framework uses signals, are actually turned into effects. So you can think about it that those effects are actually generated from the code on the right side, from the template, like automatically by the framework. And what they just did is that they hook in this even signal through this effect, which I said is similar like the computed signal. It just doesn't create another signal. It just executes this callback whenever the value change. So then this even element is overwritten its text whenever this value change, and the other change the number itself from the non-derived or non-computed. We could go line by line and see that this change when signal change, this is triggered when the even is triggered, this is again triggered because of the signal triggered. Then we assign 2 to the signal and we go again through the same cycle and again update the template. So it's like extremely efficient for frameworks to use this pattern because they are it's very easy to really precisely change things in a DOM without need to do diffing like in React or do some cycles in like dirty checking until there is nothing what is dirty, because the graph simply out of the box evaluate all the changes and it knows when it's done. Now we will go to a basic implementation, but don't worry, like the final code is like around 50 lines of code. Why we are doing it here? Because I think it's so important to understand what's happening under the hood to later realize why some usage of the signals doesn't work as you expect. Because a lot of people use signals and just handle them like some magic until the signals stop working and they are not a magic anymore, and they then struggle to debug and fix the things because the bugs are mostly on more like business level and wrong usage of the signals rather than some runtime errors. So you don't see, they are simply invisible, those errors. So let's go through so we can understand how to do that. So we will start with, or the implementation start with this like create signal function, which we saw before. And what it does is simply return an object literal, which has a getter and setter. I hope that you all know what getter and setter is, but it's actually, for those who don't, very simply, if you read a value like signal a.value, that actually trigger this getter, which return the value itself, which is like kind of private property in this case, or I pretend it is by the underscore in the beginning. And when you assign value, like value equal 8, then the setter function is called, and you could actually end up with very similar result when you simply only return value is initial value, and you have the same result at the bottom, like 5 and 8. There is no magic, no reactivity. So why we bother with getters and setters? That's because we are able in the getter and setter trigger some side effect which does something extra. It wouldn't be possible with only having this like value equal something. So why we need it? Let's go further and see. We will implement an effect, and it will be obvious why the getters and setters are needed. So on the left side, we have where we left on the screen before. On the right side, we have just as a helper the like usage of the signal. So we create the signal, and now we are creating an effect. So what we need to do to create effect, what's to be added on the left side. So let's create this function. It's get some callback here when it's created. So it's this callback. And let's say we call the callback. So we straight away go console log the signal value, and it will work, but it's just not enough yet. What it does, when we read the signal and its value, we are triggering this get value function getter, and we are able to do the hook in to the side effects. So now I add quite a lot more code, and you can see that in the getter, if we run this for the first time, we actually add this callback, which is the callback of the effect, to some set of them. You can imagine, if you are not familiar with sets, it's very similar like arrays. It just makes sure that there are no duplicates in the array. So you just add something like push, but it's just if you push twice the same or add the same, it will be there still just once. That's what we want. So that's why is it done this way. But let's go back to the effect. So when we run the effect, like the first time we actually create it, and we assign, like we create this, let's call it global variable, still maybe in a module of JavaScript, but it's accessible to both of those functions. And we assign the callback to it, then actually run the callback. So by running the callback, this function is triggered, the value is read. When it is read, then this is true because it was here we told that its callback is assigned to it, so we can actually add the callback to the set of the callbacks. So you can see that every single signal actually holds those like effect callbacks, or to be the same in case of the computed signal. We just get this callback and put it to signal. If there is a more signals used in the effect, every single signal in the effect would get the callback to itself. So it's not like the effect is somewhere aside. It will just disappear after it's registered, and the callbacks are just added to those. So at the getter, we just registered the callback, then we can happily return the value. So it does what it should, just return the value, so we can console log this on the first run. And then when the effect, when we run this whole function, is like this callback was run, we again like assign undefined to it, so this will not trigger again. So the next time the get value is read of the signal, we will not register again the callback. It's just done one time. Now when we assign to the signal new value, how the setter is triggered, we set it to this private property or private variable and the value. And beside that, we also go through all the registered callbacks, in this case effects, and just execute them. So whenever you do this, assign a value, it will know which effect contains the value inside through this pattern on the left, and just rerun it again. Now we have the very much same code, but it's now in interactive editor. So you can see that the code at the top is still the same, no changes there. It was what we left on the previous screen. And we have this create signal with value 5, create signal with value B, and now we have effect which actually used like both of the signals. So when the effect is first run, it's for the first time the callback is assigned to that let variable, and it's added to this signal as subscribed effect, and it's done the same for this one. So signal A and signal B now holds the relation to the effect. And now when I change the value to 8, so these are console logs as they were called like one after each other. So the initial value was 5B, and then I change it to 8. So this effect was triggered by the 8 change by the signal A. We have 8B, then 8C. When this change 8.4, you can see like this is interactive. When I change this to 10, you can see the console logged again were recalculated and the values propagated, this case through the effect just console logged. Now let's check what we can do with, or how we can add computed signals through what we already have. So we have signals, we have effects, and now we want computed signals. Because the computed signal needs to return signal, we use the primitive, or let's call it primitive in world of signals. So we create some signal because we know we will need to return it. And we do it here. And then we need to also call, we also use the effect primitive, and we need to call some, this will be, and now it's not a callback, it's an object, and we cannot call just callback because then we would, the value of the callback, we would not be able to assign it to the signal. So we need to pass both the signal and the callback to the effect. And for that, we need to change actually what the effect does. I changed the names here because it's no longer always callback. It could be an object as well. But beside that, it looks very similar. I just did this helper function because I cannot directly, before we just had the callback and just call it. Now we cannot call it because objects cannot be called. So we need to handle the logic and we do it in helper function. So in case the callback or object is a function, then just call it, same as before. It's just fallback for when we are still using the regular effects. But in case we actually use the computed property or computed signal, it's like the else statement which deal with that. Like for sure there should be some check whether it's like correct format of the data. It's not like when it is whatever else then function, then just do this. I don't really handle errors just for simplicity. But what I can do, I will do the callback on those and get the result of it. In regular effect, the callback doesn't return any value, it just execute and do side effect. In the computed signal, we need to return some value. So this return a value. So, and then we have on the object which was passed to this effect, we also have the signal, and we just assign the result of the callback to its value. And that's done. I again go for next screen where there is everything at once put together, including some examples with like runnable code. And you can see I again create signal 1 with value 2. We have this doublet value, which whenever one change, it will return 2. We have another computed signal, which is now not computed from the simple like first class signal, but it's computed or it's handled inside through another computed signal. So you can nest it as deep as you want. And then we also have an effect, which once signal 1 is changed, the doublet computed signal is changed, or signal computed minus is changed. In each of those cases, like each of these 3 register the callback of this effect and run it. And yeah, here we are. We have value, if we assign value 5, like this is the initial callback, we had value 2, doublet is 4, doublet minus 1 is 3. When we assign value to 5, it will change to 5, then 9. But you can see that now it's actually the first time we have like 2, 4, 3, because it was just run once, because on the initial registration of the effect, we just run it when we register the effect. So we had this once, but then because every single signal registered the effect to itself, and every single changed, because when this changed, then this changed based on it, and this changed based on this one, then it's run 3 times, and it always brings the same results. So we probably don't want it. So this is like kind of bad implementation of the signals in this case. It's not performance efficient. You can again see that when I change this, it propagates straight away and updates all those values again. So now we were able to bring very simple version of signals, and we will now talk about why it's insufficient, what should be done better. Like this is one example. We want to run this once and not 3 times, and how it is solved with the TC39 proposal. And also, based on this, and I hopefully you somehow understand it, I think I'm sure that it's just a few lines of code, but the way how it is written is probably not how you traditionally write your code when you use some frameworks. This is like, I don't know, different patterns, more advanced. So don't be aware. This presentation is online. I will send the link to it so you can go through it later. But now let's check those issues of my proposal and how they are solved in, or my solution, and how they are solved in the proposal. So issues with calculations, which we see at the end, like when signals value change, all computed signals are recalculated, and even multiple times. We don't care whether it's needed really just one time. And also it's changed even I don't read it. So in case there was no effect, then the calculations of the doublet would be still done. And I did not read the doublet anywhere, only in the effect, but so I just wasted some time on the processor for doing kind of nothing. And this is performance issue. The calculations are done over and over and just take time. And just imagine then instead of 3 signals, you have some bigger piece of code which has plenty, and you can even get to situations when then, I don't know, it's not probably good code, but you call some additional functions from there, and you can get even to some like exponential increase of the calls in some patterns, in some recursive calls, and so on. So it could be quite a disaster. So the proposal do it way more complicated way, and that's it, that the signals, when signal change, then the calculation is not done straight away. It's instead the consumer of the signal is told that its parent was changed, and then all the graph handle like in kind of some cycles, or like you can imagine just this like triple computation we did to console log 3 times the same. So we would just 3 times mark the thing as like flag it as dirty. That needs to be calculated, but the calculation is not done. Like in our case, it was like super simple calculations. It was no issue at all, but in case the calculation would be way more difficult, then it could be a problem. And the proposal then, when you read the computed signal from your application or from effect, then it's actually check whether the parent or itself is flagged as dirty, and then do the calculation. So this case, you will never do extra calculations which are not needed. They call it, as I already mentioned, like push-pull, and this is what we mostly call lazy evaluation, that something is only evaluated when really needed. Also, there can be some cases where it's actually worth it to memorize the result of the function. In case we have, for instance, number, then we check whether it's even or odd, and based on whether it's odd, we do something extra, like do the console log. But let's say like if we always increase by 1, then it's always change. But when we increase by 2, then from 2 to 4, the result is still the same. So we don't need to run the effect again, or maybe in effect it would make sense, but definitely not in computed signal, because the value is still the same. You don't need to do the calculation again to get the same result. So this is where it's handy to memorize it. If you don't know what's memorization, it's actually functional approach to caching of results and being able to return the already computed values if you are sure that the arguments of the functions are the same as before. Then we have issue with dependencies. When actually in the demo, this works quite well. Everything is garbage collected once our signals using the effects are no longer used, because the signal itself keep the effect. So if the signal doesn't exist, then the effect cannot exist as well and is collected. But it can happen that this is not enough, the garbage collection, because if our effect, for instance, handle and manipulate the DOM, and we are in some advanced single page app, we go to some other route, some other page, and then we call the effect which would change the DOM, but the DOM is not on the page anymore. So you actually need to implement some way how to unregister those effects or computed properties from their sources when if you need them. Actually, in the proposal itself, there are no effects, but there is a way how to implement them. They provide like native API of the signals by which you can create effect on your own, and it actually makes sense because in different frameworks, different libraries, you want to execute the effects in different times. Maybe the framework has some cycles, and you just want to run the effects which change the DOM at some point of the time, not like synchronously, but maybe at when all the data are for sure changed in the app, then you can run the effects and change the DOM, for instance. And yeah, so another issue is registration of or deregistration, which we slightly mentioned. And this is something which we go into next like live example more deeper, but this is like the fundamental flaw not only of my implementation, but it's actually cannot be removed. It's the pattern cannot be really changed to avoid this. And it's that if an effect is created and it's run the code of its callback, then all present signals register the effect is the same. But it can happen that some of those signals in the callback are actually not reachable in the call because of some conditional statement. And in that case, they are not registered. So this signal is not run on the first time when the effect is run or computed signal, and then the signal cannot register the signal or computed signal or effect to it. How the effect tried to handle it? It's actually try to rerun the effect registration of each computed read. So we did it that it was just for the first time when the effect was registered, we run it, the proposal and all the other frameworks which use it, I believe, or those I tried, have this same behavior that it's just a recount. But it's just, I would say, different behavior, but it's not really anything better in a matter of like missing some registrations of those callbacks. Okay, so now let's check the example. These links lead to it, but I like pre-open it because it would take time to load the whole IDE online. So we have, this is Angular code. It would be same in Svelte or I don't know, Solid.js. We have a signal, we have the computed signal, the API is different. We don't have this like dot value through getter, but it's the initiation is done here, and where the signal 1 is actually the value is used, it's just used calling it as a function, and when we setting it, it's just call a set function. But in both cases, we are able to hook in same as with getters and setters. It's just different way of doing the same. So we have the double, which in this case is computed, and there is a condition. So this is kind of like it's ternary operator, but it's like if this is true, if it's active, then run the signal 1 and multiply it by 2, otherwise return 0. So now this action pleases the things triggered from the markup. It just generates some random number and set it to signal 1. I press it and signal 1 is updated, double is updated, everything works like this because this active, which is this input value, it's active, the condition pass. Now let's change this to inactive or whatever different string than active and run it again. Now the signal value was changed, but the doubled was actually run as well, because from last time it was registered, the callback in the signal. But this time, this is not true, so it's return 0. What you need to realize that this piece of code was totally omitted. It was never run in under this condition. And that means, and also with the implementation of the TC39 proposal or Angular, other frameworks, this rerun the registration. So after this is called, it's a recheck what signals was called and update the dependencies. So even if I change this back to active, because in the registration this was not run, so this actually lost the registration. So there is no more dependency between signal 1 and the computed. So when I do action please again, nothing happened. I'm in like that end, and I cannot get back this to work again. So my derived signal actually stopped working because I did something wrong. In case this input value was signal as well, then this is part of the condition. So this signal would always be called. And in this case, in this way, the whole callback would be run again. So I can say that always when this would be changed, it would be rerun, and once this would be deregistered, next time it will be registered again. So that would work. But as long as this is not signal, the statement in the condition, then it's like no go. And this is like big issue of using signals on your own. If you don't understand what's happening with the registration and the registration under the hood, you can get to this obscure situation when the app stopped working and you have no idea why. There is no trace in the error log in DevTools. It simply stopped working and you can tear your hairs and you won't do anything about it. But let's go further. We saw the example, and I need to go back to the presentation. Okay, so now there is another issue with timing, that signals and effects are always like in my solution effect processed synchronously. In the proposal, there are no effects as we said, but signals are actually synchronous as well, but the effects can be implemented through the like low-level API in the way they need, and you can turn them to be asynchronous. Actually, I believe that it's actually done in a way that cannot even be synchronous now, that the proposal simply denied the option to be synchronous. And yeah, you have this watcher, which is this low-level API, and yeah, if you want to run it, you actually need to queue it to microtasks, which is something what's run in this like mythical event loop of JavaScript, how the code is actually executed and handle how the code is run again and again. But we are not here to understand or explain how task, microtask, and queue work. So let's go further. So what's about the proposal in general? It's in stage 1, so it's one of, I believe, 4 or maybe 5 stages. So in the beginning, but it goes quite fast. It took like months to get from stage 0 to 1, and there is already discussion. It looks very promising. It tries to be very minimalistic, so it doesn't try to bring too much, but rather start slowly, and maybe things will be added later. It has some extra API beside the signal and computed signal. It has this watcher and also unwatch, which enables the effect implementation. It has untrack, which you can understand like when you have computed signal and you will use 3 signals inside, which create those dependencies, but maybe one of those signals used inside, you don't want to trigger the recomputation. So you just wrap it to untrack, and then whatever signal is used in some computed signal and is wrapped in untracked, it actually doesn't trigger the recomputation, doesn't trigger the callback of the computed property or effect. And then there is also some API, which I don't really see why it should be accessed by a regular developer at all, and just tell you what are the relations between those signals in the graph. It can be used in some like extreme situation of some frameworks that they want to clear the graph like beyond the regular like unregistration of signals. Okay, and now the question is whether you should use signals. We have seen that signals are used in a lot of framework nowadays, but they are actually used mostly under the hood, and they are used there from, I don't know, Knockout maybe use it, I believe, long time, it's more than 10 years probably, but they all use those as like pieces of the internal API, how the framework updates the DOM. And now it's changed, and frameworks like Angular, Svelte, and others are coming with those signals to expose them to the like developers to use them on their own. And as we saw with the condition, which can register your dependencies, it's not that like it's easy to make mistake, and there are other mistakes which can be done with the untrack functionality, where you also can get lost some dependencies, and without knowing what's happening under the hood, this could be quite dangerous. So yes, I believe you should use signals. Don't be aware. Like I didn't want to discourage you by what I was showing, but try to keep in the signals, like especially in the computed ones, and affect really simple pieces of code. Don't try to do some logic there. Just do the basic computation, how more signals are mapped to some derived signal, but don't try to use condition inside. Don't try to use some like calling to some other functions outside of this, bringing some dependencies to dependency injections, or like messing around, because then it will be like super hard to debug. Hopefully there will be some once or if the proposal will be fruitful and it will land in JavaScript. They already promised work on some dev tools which can help you in showing actually the graph of all the signals in some like visual way. And then it would be obvious if you see that something was registered, that the relation is no longer there. So it wouldn't be that hard, but also not that easy. So yes, use signals, but be like really precise and don't don't use them for accessing like excessive solutions. Yeah, so that's it from the presentation. So it was more like helping you to understand what's happening under the hood, what's the pattern inside, and now it's time for questions.